In this lesson, we're going to look at another transformation of the plane called a reflection. So when you look in a mirror, you see a reflection. If you move closer to the mirror, your reflection moves closer. If you move farther away, your reflection moves farther away. And if you touch the mirror, your reflection does as well. Mathematical reflections behave in a similar fashion. To define a reflection, we just need a line called the mirror line. So let's say our mirror line is vertical like this one. When we reflect a point through a line, it moves to the opposite side of the line, keeping its distance from the line the same. And if the point is on the line, just like if you touch a mirror, it doesn't move anywhere when you reflect it. So here, we have the point A, which is on the left-hand side of my mirror line, and it reflects and goes to A prime on the right-hand side. And it's exactly the same distance from A to the mirror as it is from A prime to the mirror. Or at this point B, which is on the right side of the mirror, reflects and goes over to the left, keeping its distance from the mirror exactly the same. And if a point is on the mirror, its reflection is exactly the same point. So if a point C here is on the mirror, C prime is the same point as C. It doesn't move anywhere. And here's a happy dancing man on the reflection line. Before we go on, we should be precise and define exactly what we mean by when it goes to the opposite side of the line, keeping its distance from the line the same. So let's say my mirror line is this line L. This cursive L is a traditional name that you give for lines in geometry. So if A is a point and A prime is its reflection through a mirror line, then the mirror line L is the perpendicular bisector of the segment connecting A to A prime. Let's look at that. So I'm saying that L, the mirror line, is the perpendicular bisector of the segment that joins a point to its reflection. Perpendicular here means that the line, the mirror line, and this segment form a right angle. And this is kind of what I mean by saying A prime is directly across the line from A. Bisector means L divides A prime into two equal parts. To bisect something is to divide it into equal pieces. And so that means that the distance from A to L is the same as the distance from A prime to L, which is the other key feature of a reflection. So when you're doing reflections by hand, there are some techniques that I'm going to show you in the example lesson. So you should look at some of the examples. For the rest of this lesson, I want to talk about how we reflect points in a coordinate system. So in general, when we reflect points in a coordinate system, the formulas get really complicated. So for example, if I had some line like y equals 3x minus 1, and I wanted to take some random point A and reflect it, the formulas that tell me, okay, here's the A, which is at 3, 2. How do I figure out where A prime is? These are very complicated formulas. We're going to learn a little bit about this in second semester. For now, we're going to learn how to compute reflections through three types of lines. Through horizontal lines, those are lines where y is a constant. Through vertical lines, lines with an equation x equals a constant. And then through the very special case of the line y equals x, which passes through the origin with slope 1. Let's look at how you reflect through these types of lines. First, a horizontal line. So when a point is reflected through a horizontal line, it's going to move vertically to the other side of the line, keeping its distance the same. Since it's going to move vertically, its x-coordinate stays the same. Let's look at this one piece by piece very carefully. Here's a point A, and let's say we want to reflect it through the horizontal line y equals 3. So this is the line that is 3 up. That's the horizontal line, y equals 3. It's 1, 2, 3 spaces up. So when we reflect this, because this line is horizontal, this is going to move vertically. And it's going to keep its distance the same from the line. It's just going to go to the other side of the line. So since our point A is 4 units from this horizontal line, we can just count it out, then its reflection is also 4 units away. So A prime is right down here and apparently has coordinates 2, negative 1. And this is a summary of what I just walked you through. You can determine the coordinates by drawing a careful picture and counting off units. Another way you could do it is you could use arithmetic. The original point A is at 2, 7. That's this point's coordinates, 1, 2, 7. Since we're reflecting through y equals 3, this point here is 4 units away from this line, because this point's y coordinate 7, and we have y equals 3, the difference is 4. Therefore, the image has to be 4 units below the line. And if I go 4 units down from y equals 3, I get 2, negative 1, because 3 minus 4 is negative 1. And notice, since we're moving vertically, the x-coordinate remains the same when you reflect it. Reflecting through a vertical line is very similar. The only differences are the equation of the line is now going to be x equals a constant, and the point is going to move horizontally across this vertical line. So here we have the point A. We could draw a careful picture, realize it's 3.3 units from this line, and so its image is 3 units from the line on the other side. Or we could do arithmetic. This point's coordinates are 2, 7. 2, its x-coordinate, is 3 units away from negative 1. So therefore, its new x-coordinate is going to be 3 units away from negative 1 on the other side at negative 4. And that's what we see. Its new x-coordinate is negative 4. And of course, its y-coordinate remains exactly the same because it's moving horizontally, keeping the same y-coordinate. The last type of line I want you to be able to reflect through in this unit is the line y equals x. That's the line with slope 1 that passes through the origin. It makes a 45-degree angle with each axis and passes through all the points with equal coordinates, like it passes through 2, 2, and 3, 3, and 3, minus 3. This is the line y equals x. You can determine the coordinates of the image by drawing a careful picture. Since this line is diagonal, the point is going to move diagonally. It's common for students to want to make it go through the origin here for some reason. It moves straight to the line like this. And we can count the diagonals of the square to see how far it is away from the line. 1 diagonal, 2 diagonals, 2.5 diagonals, so its image is on the other side. However, there's a very straightforward shortcut for reflecting through this line. When we reflect a point through the line y equals x, the image point has the same coordinates as the original but exchanged. It's a very simple and useful shortcut. In other words, since this point has coordinates 2, 7, its reflection will have coordinates 7, 2. And that saves a lot of trouble in drawing a careful picture and counting diagonals if you can remember this useful shortcut to just exchange the coordinates when we reflect through the line y equals x.